All right, welcome back everyone to Mastering Shiny book club. And today we are going to look at the performance chapter, which is the last chapter of the book. In the performance chapter, the book discusses how to benchmark your app using the Shiny Low Test package. There is a section in the slides here that also shows you how to use Google Lighthouse for auditing the performance of the package in terms of accessibility and the timing, although it's not in the chapter. And then we also learn how to profile the app using the ProfWiz package and also Shiny TikTok package. And then finally, how could we optimize the app using different methods? So let's start with benchmarking the app. And to explain that concept, the chapter uses an analogy of a restaurant. Uh, so here in the analogy, our server in the Shiny app is like a kitchen in the restaurant, and the user is like a customer. The request that we send to the server, for example, to create a plot and render it, is like an order in the restaurant, and the R process that contains that server or that manages that server is like a chef in a kitchen. Here in the image, we see that there could be multiple simultaneous users that could be accessing our app. And if our app is running a single process, it is then single-threaded. And in a single-threaded app, a single-threaded programming language like R, things happen sequentially. And so if one user, the first user that accesses the app, is going to run a long running computation, for example, for 5 seconds, then other users will have to wait until those 5 seconds are complete, and then they'll see their own results. And the timing, if they are using the same process, would be 5 + 5, and so on. With async programming, we can adjust this, which we'll discuss momentarily at the end of the discussion today. So how do we make our chef, our server, and our process more efficient? The first thing that we should do is profile the app, which means that we watch the chef when there are bottlenecks, and then optimize. Once we know where are the bottlenecks, we can brainstorm ways to work faster. We can hire another cook, which means that we have someone working in a different R process, or we could have some data loaded even before the session. So at the launch of the app, the time it takes to load the data and prepare the data would be longer, but that's only for one time. Every time a new session starts, that time is already taken before, so it's not a time experienced by a new user. Invest in a time-saving gadget, for example, a faster R package. Example of that could be Collapse, which is very similar to dplyr or data.table. If we have a lot of data manipulation processes that we have to have in the server. And adding more chefs, which as I said before, and shown here in the example, we could have multiple R processes, which could be like Docker containers that run the same app in different processes, or it could be through async programming. So to solve those limitations, we have two options or alternatives. One is scaling up, which means that we are upgrading our equipment so that we have more memory or more number of CPU cores, and we use async programming to divide or distribute the calculations. Or we have multiple R processes that we use, which is scaling out. Let's start with benchmarking. For benchmarking, we need to stress test our app. So when the app is running and multiple people are using the same app simultaneously, we want to see how our app behaves, how long are the timings that the users experience. Shiny load test package is very useful for that, and it has 3 steps. The first step is to record a script simulating a typical user, and for that we have the record session uh, step from Shiny load test. Then, once we have gone through that, we replay the script, but this time using the Shiny Canon tool, which is a command line tool. We don't use it through R, we use it using command line, and it is based on Java. And then with Shiny load test again, we generate the report to find out how the app does. So let's do these 3 steps. I'm going to share my screen again. I'm going to share my RStudio. If you don't see it, please let me know. And the first step here is to run our app. So let me first show you what the app looks like. So I'm going to run the app first without Shiny load test. And you probably don't see my window. Let me share screen again. So this is an example app that I created that contains fast operations and slow operations. So the first one is fast operations where we're just squaring a number. So this is pretty quick. With slow operations, we have matrix and we are summing all the values in the matrix. So this takes a little while to get us the results. And the final one is to generate plots. So this is the app that we want to test, and we want to see how it does when we have multiple users accessing it and using all of these simultaneously. Close this and switch back to RStudio. And I'm stopping this app. To use Shiny load test, the first step is to run this app in a background process or in a separate process so that we have this app continuously running. So to do that, we can use Shiny run app in the terminal. So I'm going to do that here. And notice that I'm using port 5555. I run that. And I'm going to copy this and then run that here. What did I miss? Oh, I didn't copy it correctly. Yeah, Control C is going to stop in the terminal. That's why. Anyway, I can copy it from here. And now I'm going to use the app as my user would. So I'm going to click on this, look at the results. Then I'm going to calculate slow matrix computation. Maybe I change a value. And then I look at the results. So it's important that we simulate how a typical user would behave. And then I'll generate the plot. And then I take a look at the plot. All right, assuming that this is how my app is typically used, I'm now going to go back and I actually should do this when I'm running this. So currently, this is the app running in the terminal, and I open it and use it, but I should do it here with the record session. Sorry about that. Run this, and here I'm going to reuse the app. Okay. So now I can close this tab and return to my RStudio. And now I can see that client is disconnected, stopping the server, and there is now a recording.log that is generated. Now in step 3, I need to replay this, but this time assuming that there are 20 people using the app at the same time. And in this case, notice that I am using the command java -jar shiny canon. The installation instructions are provided in that chapter. The shiny canon is a file that we need to download and put in the same folder as I did here. And then I use recording.log that is generated for me. And I say --workers should be 20, which means that 20 users are simultaneously using the app. Then loaded duration minutes 1. This is the typical duration that we expect the user would be using. In my case, I did it less than 1 minute, but I'm going to do 1 minute, and it would repeat the simulation for the time that is left. And then my output directory will be called as test20. Where we'll have all those results. As you can see here, I have test 5, where I already tested this for 5 users before. I'm going to run this. And since my app is still running, as you can see in the terminal, and it has to be running for the Shiny Canon process to work, I am going to create a new terminal. And I'm going to then run Shiny Canon command here. And so this will take some time, and this will create the results for us using those 20 users, 1 minute each. So while this is running, I can show you what are the next steps. So in the next steps, once we have this process completed, we can run load_runs function from Shiny load test, and we can provide it with that folder. So currently we have test 5 and test 20 folders. Test 20 will eventually contain all the results from this process. And I call it as benchmark_data. And then I'm going to use Shiny load test_report function. And I'm going to use my benchmark data to generate a report called as explore.html. I currently have the report when I ran it for 5 users. So let's take a look at that. So the most important plot here is the session duration plot. There are many others, but to save time, we are not going to look at those today. So on x-axis, we have the time since the session started in seconds. And on y-axis, we have each user. So these are sessions. Each user creates their own session, and they're ordered by the total duration. So here we see the red line. This is the time that I took as the typical user when I first used the app when we were doing record_session. And then the rest of it is representing 5 users. The first thing we see is home page. So this is the time that the home page takes to load. In this case, we see it is pretty fast. So it's not something to be concerned of. The next is JavaScript or CSS. In this case, because the app is very simple, it only uses the default JavaScript and CSS. So we don't even see the time that it takes to load those. Then the start session. We see for some users, these are probably the third and the fourth users who have the start session taking a little longer than others, but still not too big. And the rest of it is the calculation step. We have 3 types of calculations, and for each user, we have different timings. So this is probably the matrix computation for all 5 users. The good thing about this usage of the app with 5 users overall is that everything here is less than the typical time that I took for when using the app with record session. So this is a good indication that the app is pretty fast and we don't really need to uh, make anything faster. But if we do get results for the 20 users on time, then we can test that. Uh, I didn't see any failures before, but with 20 users, I now see some failures. So there are 13 failures. I'm not sure why, but let's see the results of this. Okay, maybe I should comment this out. By the way, I'm using the development version of Shiny Lotus because uh, the CRAN version has some bug in it. It was not generating the report. Okay, so here we have the result for the 20 users, and for session duration, we now see that probably this 19 or 20th user, they have more timing than the typical time that I took, which means that this app can easily incorporate like 15 users simultaneously. This is a pretty fast app. They don't have to wait for a long time, but at least it does provide us some idea of where we should look at if we want to optimize something. So we see that these functions are taking longer, and we can actually look into more details for each event and for each user. Any comments, any questions at this point?
Nope, nothing for me. Looks really cool though.
Okay, thanks. Let's go back to the slides. Okay, so we've covered all the steps for the benchmarking. Um, Next is auditing the app, which gets us more information about accessibility. And this, I think, only works on Google Chrome. So if I run my app again, and this time I'm going to just run it directly from here, and I'm going to, so this browser that you're seeing right now, this is Edge, but I'm going to run the same app in Chrome. And let's look at all the results. And when we inspect here in the menu, we can access Lighthouse. And we have some settings here. Right now I'm using desktop, so I'm going to click on desktop here and then analyze the page load. And we see that the benchmarks are pretty good, 100% performance, 94% accessibility, best practices, and so on. For my actual app, it doesn't really work that well, but yeah, for this simpler app, we see good results, and it has some diagnostics, eliminate render blocking resources, which I don't think we can do that because the blocking is happening when we have longer computation. Reduce unused JavaScript. So some JavaScript is loaded when Shiny is loaded. This is part of Shiny. I don't think we can reduce that, and so on. So uh, there are also talks about Lighthouse on Shiny conference talks, which are available on YouTube. If someone is interested, check them out.
Sorry, that actually looks really interesting. You were saying there were Lighthouse talks from PositConf
From
or just
ShinyConf.
on from ShinyConf? Okay,
Yeah.
cool. From last
ShinyConf.
year's or this year's?
I watched one from 2024.
2024? Okay, cool.
Yeah.
Thank you so much. I'll look into it.
Next step is profiling. So once we see what is probably so not the what, but once we find out that the app is not performing well, we need to find out what is it that's slowing the app down. And so here we have some examples of profiling using the profvis package. So to look at that, we have these three functions. The function f pauses everything for 0.2 seconds, and then calls the function g and function h, and then returns the number 10. The function g itself pauses it for 0.1 seconds, and then calls function h, and function h then pauses for 0.3. So if we run this and we do profvis on the function f, it will tell us the timings of each of these functions. That helps us understand what is going wrong. Maybe I need to rerun this. Yeah. So here we see that we have the function f, which is obviously taking the longest. Then we have the function g, and then h at the top. So this helps us understand that overall f is going to take about 0.9 seconds, which we can see here at the bottom. G is going to take about let's see. So in this case, G has 0.1 seconds here and 0.3 seconds here. So 0.4 seconds are for G, which we can see here. If you look at the tooltip, it says 390 milliseconds. And similarly, we have H, which has 590 milliseconds. This is aggregated based on the two runs. So this can help us understand, okay, this function is taking longer, and we need to work on optimizing that particular function. This is outside of Shiny, but we can do that with Shiny app as well. We have the same functions in the app now, and we are running profvis by wrapping the run app function, which itself is wrapping the Shiny app function. The rest of the code is the same, and it's just that we are generating an output y using the event reactive. So the output is a text output, which we render here. So let's run that. And when I click on push me, it generates the number 10, which is the result of a function f. And now when I close it, we should get the profile. So here, because it's a Shiny app, there are multiple functions at the bottom, as you can see here, and we see the actual functions that we are interested in at the top of the tower here. And that's because Shiny also runs other functions, other services. That's why we see all of these. We get that same information here, and this tells us that F is taking the longest, and then G and H, and we can further optimize these functions. Another way to optimize or to profile, sorry, the app is to use Shiny TikTok. Shiny TikTok is not a package, it's just a script. So all we have to do in the app before is just put this line, which contains the source to the Shiny TikTok JavaScript file. Everything else is the same, except now we don't have to say profvis. We can just directly run the app as before. And when I run the app, This time I'm going to launch this in the browser. Like push me, get the result, and now look at the inspector tools. Go to console, and from the slides, I'm going to copy a command. This is a JavaScript command, await export HTML report. And doing this will download a report, as you can see here. If I open this one, here we see the timings for the server computation. We see there is some computation that's happening first, and then after some delay, there's another computation. And this one is the output, output Y. As we discussed before, this is the output Y. So this is function F, which is going to take a total of 0.9 seconds, which we see here. So this is about 905 milliseconds. So this is another way, an alternative to Prof is to profile the app. And you can imagine if you have lots of outputs, lots of functions, then the y-axis will be longer. So how do we improve performance once we find out what is causing the bottlenecks? To speed up our app, we need to first isolate the problem in a function, which is if we are writing functions for each task that we do in the app, make a minimal snippet of code to recreate that slowness, write a few tests, as the easiest way to make code faster is to make it incorrect. And run this snippet multiple times as you try out possible improvements. All right. Okay. Next step is caching. Sometimes we don't have the option to make our functions or calculations go faster because they are just the nature of the calculations is such that we cannot. So we can cache our results, and there are many different ways to cache those results. Bind cache is Shiny's own way to do that. So here's an example where we have two inputs from our user inputs in Shiny, and we have some slow function that uses those inputs. Now, if we use bind cache on this reactive expression, we need to provide it with cache keys. Cache keys are those inputs that affect the calculation, or those are the inputs to the function. So if we use bind cache, then for all the users of the app, for the same R process, the results will be cached. So the next time the user looks at the same result again, they'll see that the results are cached, and it wouldn't take longer to get the results back. And here is another example where instead of the reactive expression, a rendered text is cached using the bind cache function. In this case, there is only a single input. So here we have an example with a web API. Let's see that in action. I'm going to stop this app, and I'm going to first show you what it does. So I'm going to load the per package, and we have this function called latest events that uses the GitHub package, and it takes in a username of on GitHub, and then it will look at the repo and the type, and it will give us this result. Because it's a web API, it will send a request and then get some results back, so it takes some time. So we run this function definition, and now if we time it for the user Hadley, we see that in this case, it's taking about 0.05 seconds. Now, let's run this in the app. And this time I'm going to cache the results with bind cache. So we are getting the latest events, putting it in a reactive expression, and then caching it. We'll talk about system.date later, so I'm gonna remove this for now. Keep in mind that latest event uses the username, so we provide that as an input. And because the caching key here is username, every time we change it, it will cache the results for that username. If I type Hadley here, we get these results. And let me try this, so we get the result. And now if I go back to Hadley, now it is quicker than before. We don't notice it a lot because it is already pretty fast, but it will be quicker because this result is now cached. We can also put system.date as an additional variable, as an additional cache key. And that's because if we expect the data to change every day, like in this example, we do expect that because it's a GitHub data with new commits, we expect that it would change. We can just limit the caching to a given day so that it doesn't look at the previous data. We can also cache the plots. So let's first look at this example and then we'll go back to the code. So in this case, you could see that it took a few seconds to load this plot, which is on caret and price variables. If I change this to cut, now we are looking at that. This is a pretty quick plot, but going back to caret, now it is very quick. And then that's because we have cached it. So let's look at the code. We have a render plot where we use ggplot and we use the input x and input y, which are the two variables, and we bind cache using input x and y. If I comment this out and rerun the app, so notice there's some time lag for loading the plot. I'm gonna go to the cut plot and then go back to the caret plot, and it still takes that time. But with cache, it didn't. So let's look at that again. So it is pretty quick because it's just loading that data from memory. So bind cache by default uses the memory. So this node is important. The cache has a fixed total size, so it won't accumulate data from previous days, and is smart enough to automatically remove the least recently used data when it needs more space. So it will keep deleting the data if it goes above a certain limit, which is 200 megabytes. And this is the day thing here is referring to sys.date. Another important caution here is that if we have two inputs that change the reactive expression, then in the bind cache, we should use both the inputs, not just one. Because if you use just one, it will use the input y from before. Sorry, it will use the input x from before, but not input y, and will get unexpected results. So as I said, bind cache is not going to use more than 200 megabytes, and it will delete the older data. It is also lost when the app restarts. That does not mean that when the app is launched in a new tab, there's just a new session. App restart means that you've globally restarted the app. We can also use disk caching. using the cache m package with cache disk instead of using memory caching. And for that, we can use this function shiny options cache equals cache underscore disk. Another important point is that if you have different types of users and they have their own data, then caching the data globally doesn't make sense because one user is not going to look at another user's data. And so we need to cache only the session, which means that we need to specify cache equals to session for unique data for each user. What other optimizations can we use to make the app faster? One thing we can do is if we have any preparation step, which takes longer because we may have some slow function, instead of doing this inside the server, we can do that outside within a global.r file or within the same app.r, but before server. So this will happen only when the app first launches. Then for reading, we can use data tables fread. We can use the room function. Now we also have arrow, geo arrow, duckdb. So those make reading data faster. Instead of read RDS, there's a QS package that has qread and qsave functions that are also faster. And they are for data which are not data frames. We can also manage user expectations while our app is loading with large data. And for that, we can add spinners. We can split our app in different tabs because when the app launches, only the active tab, the data there will be loaded. For other tabs, the data won't load unless we open those tabs. So that also saves some time. And we can use the Raider package or now Shiny's own bind reactive, not bind reactive, it has particular function which is available in Shiny 1.9, which will have its own spinner. I think I can quickly find that. Shiny 1.9. Probably in the change log. Yes, it's called use busy indicators. If we have this in our UI, then it will automatically use a spinner for the slow loading data instead of just graying out as Shiny did before. And if we want to do async programming to run a task in a different R process, rather than blocking the current R process, we can now use extended task with the packages future and promises. Previously, there were only future and promises that we could use or call our or Mirai packages. Mirai also has another package called crew, which manages the Mirai processes. But extended task makes the syntax much simpler, and we can use it to manage async examples, async tasks, sorry. So let's see one example of extended task. So since we are going to use multiple processes, I'm providing here workers equals 2 with strategy equals multi-session under the plan function. The plan function comes from future package. So notice I'm loading the future and the promises package. We provide that plan, and then here in the app, we have the input task button, which is the replacement of action button from Shiny. And input task button is a function from the bslib package. The advantage of using the input task button is that it will show processing while something is processing and is bound to that action button. Action button by default does not have that. And then we have some numeric inputs, a text output that shows time, and a text output that shows a result of creating a normal distribution. Here's how extended task going to manage this asynchronous programming. The function that we want to run, in this case, we want to generate a normal distribution, is right here inside future underscore promise. To make this function run slowly, in the example, we put system.sleep 3 for 3 seconds. Everything is wrapped inside the future promise, and then we bound it with the task button. This is equivalent to using observe event and observe event launch, and then within parentheses, we put everything from here. So we are using future promise, and this would, the future promise section, this part, this will not return the result of our norm. It will return the result of, it's going to return something called as a promise, which means that whenever it is evaluated and is available, then we can get the result. Before that, we will wait. And this is wrapped by the extended task new. New is the extended task is the class. So extended task new will take in this function. And here in the function, we provide what is it that we want to run. And we are binding it with a task button or an action button. This is optional for this example, but this clearly will show, as we'll see momentarily, how effective this is, because here we are going to just show time, but you will see that because our main slow running task is going to go into a separate R process rather than the main Shiny app process, the time won't stop, it will keep running. And once we have created this task, we give it this name, and now we are going to use invoke method from extended task, and we give it the input. Input in this example is just the numbers, how many numbers we want to generate for normal distribution. And then finally, where we want to show our result, in this case, it is render text. So we render the result of normal distribution by getting the result method from the ET norm extended task. So let's run this. By the way, here I see this message since I'm running this in Posit Cloud. It doesn't have more than one CPU, so it only has one CPU. So it warns me that using two localhost parallel workers, but we only have one CPU. So it's probably not a good idea to run it here, but this tells us that we need to be careful about the machine hardware. So here I am saying how many numbers I want to generate. Notice the time is running, and I'm going to click launch computation. Now, time does not stop running, and I get the result, which means that this task ran in a separate R process, and the time is running in the main R process of the Shiny app. So one question that I had here was, what if I want to bind cache this result? So every time I change the value of our norm size, the number of outputs, it will recompute it. What if I want to cache it? So we cannot do bind cache directly on this, but we can use the on-disk caching using the Memwise package. So here is the same app again. This time we are going to use the Memwise package, and the function that I wanted to run was system.sleep and rnorm. So I'm now wrapping it with Memwise, and I specify this argument cache, which is Memwise cache underscore file system with dot cache. This will store the result on disk. And now I can use this R norm cached inside extended task instead of R norm only. Everything else remains the same. And now I'm going to run the app. So I launch this computation and I get these results. Notice the first number and the last number. So 1.45, negative 0.74. Now I'm going to change this to 1. So this takes some time to compute this. And now I'm going to change back to 10 and launch computation. And now it didn't take time. So we get the results back fast. In all of these processes, the time didn't stop, which means that whenever needed, we are running the computation in the background. When not needed, we are getting it from disk. Right, so I think that's the end of the chapter. Any questions, comments?
Just for my part, wow, you blew my mind. Lots of cool stuff there. Thank you so much for it. I really profited from having you explain it all. I have to run to another appointment, so I got to leave right now. But thank you very much. Is there
Take care.
another session after this, or is this the last chapter?
This was the last chapter for this cohort.
Okay. Okay. Well, I know I kind of missed the bus on this cohort, but maybe I'll see you in some future cohorts. So thank you so much.
Yeah,
Good
welcome.
for you.
Take
All
care.
right. Take care.
Derek, any questions?
No, nothing at the time, but just wanted to compliment you for putting in all the work and really showing various demos of how these performance issues can appear. Thank you.
You're welcome. I'll put this project link on the Slack channel. Okay.
Right.
Okay. Thank you so much for attending and keep in touch.
Yeah, it's good. Thank you. And yeah, see you later.
Stop.